Hello, and welcome to the Matter lecture. This lecture is going to go over the matter, its states, its properties, and its structure. Now, this is our first video for the year, so we're going to go ahead and go over the general procedure for these. With each video, I'm going to be trying to teach you a specific concept, and we're typically going to have to define the terms in that concept, and that's going to be later expounded upon with things that we can do to mess with that concept in general. Now, our concept today is matter, and matter is something that you should have encountered a couple of times, hopefully in middle school. We're going to go ahead and review it here. We're going to talk about some interesting facts about it, and then we're going to talk about the particle structure and how the particles of different forms of matter interact, and that's really our main goal in this discussion right here. But to start, we have to go ahead and begin by asking, what is matter? And whenever we're going to have a question like this, we're going to have to first define it. And we define matter as everything that has mass and takes up space. So if something has a mass to it or it has a weight to it, that is defined as matter. If it does not have a mass and does not take up space, that is non-matter. And typically when we think about these things, we think as matter as different objects that we can interact with. And the opposite end is that non-matter is typically something that we think of as energy. And these two things are related to one another. In fact, they're related to one another in the famous equation of E equals mc squared. And E equals mc squared is important for us because it shows how matter can be turned into energy, but also how energy can end up being turned into matter. Now, the most famous example that we have of E equals mc squared is through nuclear fuel or nuclear weapons. Both of those end up taking a small amount of some sort of nuclear material. And a nuclear material is just some radioactive material that decays into two different elements, and when it does that, it loses a tiny bit of mass. And that mass is what this m is right here. This c number is the speed of light squared. So it's mass times the speed of light, which is really, really, really fast, squared. So that's a lot of energy. So any tiny amount of mass that gets transformed into energy is going to give us a lot of energy. This is the way of going from mass directly, converting that tiny amount of fissionable mass to energy. But it can also end up going the other way. Many of you have probably heard of the Large Hadron Collider in CERN. And the Large Hadron Collider in CERN is concerned with making, in particular, matter. And how it does that is it spins these two photons, or very, very tiny particles, in a very large ring, and it just tries to give them as much energy as possible. And then when they have it collide together, the hope is that that collision, that incredible energy that is in that collision, is going to end up creating different forms of matter that they can then therefore be tested. And one of the things that's important about this is that they can go ahead and directly convert the energy used to make that matter into the mass of that particular object, which has different functions for how the entire universe works. So that's why we're doing those sort of experiments at CERN, and it's because of this E equals mc squared equation being useful for us. Now that we've defined the types of matter, we can go ahead and look at the different types of matter. And the different types of matter you guys are already familiar with. There's solid, liquid, gas, and plasma. Now, solids, you guys are already very familiar with solids. You know, they feel like a solid. You can pick up a rock, that's going to be a solid. Liquids, hopefully everybody's drinking lots of water. And gases, well, you may not consciously interact with gases, but you are breathing in gases all the time. Plasma, at your age, I definitely hope you haven't been interacting too much with plasma, because plasma is really just a superheated type of gas to the point that it has started to lose electrons. So it has an extreme amount of energy to it, which is why we end up having to have its own state of matter, because it just functions so differently from a normal gas, and that's mainly because of how much energy that there is. It has ended up stripping up some of its electrons, and that ends up affecting a whole bunch of the properties of how it works. Now that we've defined matter, we can go ahead and talk about the particle structure of those different forms of matter and some of the properties that are involved there. And in general, we're going to take a look at each one, and there's a couple of things that I need you to know about these going forward. We're going to start with solids. And solids, you should know that solids are very, very tightly packed. Like, the atoms that are in solids are very close together. They're so close together that their movement is kind of restricted. And they're restricted in this way that they can only really vibrate in place. So this is an example of a solid. Notice that it's really, really tight. And all of those molecules that are in there don't really have much of a place to move to. Another thing that adds to the fact that they don't have a lot of space is that they are not compressible. So, since there's no space in between here, you really can't press on this object and make it any smaller because there's not a lot of room there to press it. Another function of this is that there is a definite volume to all solids, and they all have a definite shape. The shape of a solid doesn't change depending on what type of container that you put it on. Now, I also wanted to show you here how a solid moves. And this is an example of how a solid moves. Notice that all of the little dots, this dot right here in particular, isn't moving very much. It can vibrate and it still has motion, but it doesn't move at all. So now we're going to go ahead and go back to our presentation here. And after solids, we're going to go ahead and go over liquids. Now, liquids are going to be more loosely packed together. And this is another example where we have an image of the liquids. And you could see that some of them are pretty close together. But, you know, there's some free space in between here. Liquids, in general, when we talk about their movement, we like to say that they're able to slide past each other. So, they can slide past each other because they're not super tightly packed there. They've got a little bit more room to wiggle in between there, and they can get past each other. They are only slightly compressible. So, liquids in general, we could theoretically press on it, and instead of it taking up this whole space, we can condense down a little bit of these and get them to lower down right there. Liquids, we know we have a definite volume. If you take 200 milliliters of water and you put it into a different type of cup, if you put it into a styrofoam container, you're still going to have 200 milliliters of water. And they have an indefinite shape, which means that it ends up filling any type of container that it exists in. so its shape is able to change. This one as well, we do have an example that we can go ahead and look at. And this is an example of the movement of a liquid in a container. Notice that they're all able to move. They're still in, the same general area. They're not going wildly all over the place. They're just sliding past each other. They've got enough energy of movement that they can slide past each other quite easily, and they're not kind of locked into one position there. The next one we're going to look at is going to be gases. Gases end up being far apart. Now, a gas is going to be farther apart. It's nowhere near as densely packed. So you guys can tell we're always walking through gases in our everyday life. It doesn't feel like there's much resistance there at all until you get going really, really fast, and then you can start to feel that resistance. Gases also end up being energetic, and they bounce apart from one another. So when gases end up hitting each other, they end up bouncing because they have so much energy. And also they are highly compressible. So think, all of this is empty space. You could compress that down to an incredible degree, and there would still be plenty of movement for these gases to go ahead and have in there. And because they're highly compressible, we say that they have an indefinite volume because they will end up filling their container. Gases will fill whatever container they're put into. And we also say that they have an indefinite shape. They're going to fill up any shape possibility that is possible. And this one as well, we do have an example that we can go ahead and look at where the gas is right here. You can see that they have a lot of room to move around. When they do collide with another gas, they bounce off one another, and it's just how the gases work right there. The last one that we're going to cover is plasma. And plasma is very similar in the energetic set that we use in gases. So the molecules are very similar in the fact that they're very spread apart, or they try to be spread apart, and they have a lot of energy. But they end up having so much energy that they can actually knock electrons off and end up being a charged ion in there. A couple of the things, they have no definite shape, they have no definite volume. So the same rules that apply to a gas end up applying to a plasma as well, which means that they can be compressed. And you guys have already seen an example that has a bunch of compressed plasma. In particular, if you look up at the sun, which don't do it without proper protection and don't look directly at the sun, but that's an example of a gas, a plasma type gas that's being compressed down. And the sun is essentially just a big ball of gas, and in the inner core of the sun, you're going to find that there's a whole bunch of instances of plasma. Now, you can end up seeing plasma in other ways. Most often on Earth, if you ever get up north, especially during in the countries of like Iceland or in Alaska, you can see what's called the aurora borealis, and that's where you end up having some ionized gas in the atmosphere, and it ends up changing colors in the atmosphere. Anything that involves any sort of fusion and lightning can very briefly impart enough energy to ionize the gas that's right around it. Okay. And these are going to be the different factors or the different ways that these particles interact, and this will give and it's essentially the properties of these gases. So this right now is going to go ahead and close us out for the first matter lecture. Make sure that you have your notes good and set, and then I will see you on the next one.